If you're shaking your head, I'll try to acknowledge the fact that you are shaking your head. Okay. So we'll get started. There's something I want to say. Oh, so I'm recording these videos here, and I will post them to YouTube, and I'll have a link on the web page. There should be a little page that says lecture videos. And again, they're here to help you, so if something didn't quite make complete sense the first time around, you can rewatch the video, and I hope it will make sense the second time around. And yeah, we'll figure it out. Okay. Alright, so here we go. This is chapter 1. We're covering chapters 1 and 2 today, and we will talk about statistics. Alright, so that's what this class is all about. And I always get really excited every time I teach a new class. I always get this like butterflies in my stomach. First class. And well, because it's always a new group of students, and I'm always hoping that that you will enjoy this class, okay? When I took my first introductory statistics class as an undergraduate student, it changed my life. It literally changed my life. I was studying engineering. I finished my engineering degree, but I fell in love with statistics along the way, and so here I am today teaching statistics and pursuing this as my career. So I don't know if you will have such a transformative experience in my class, but I hope at least you will appreciate the subject here. Okay. So what is statistics all about? Why do we study statistics? Okay. So, my argument is that you would study any subject matter to help you understand the world around you. So, we study history to understand the world around us by learning about the past. We study biology, chemistry, and any of these subjects to help us understand the world. And statistics, in the same way, allows us to understand the world around us a little bit better. In particular, okay, statistics. And in particular, statistics allows us to draw conclusions from limited data. What does that mean? To draw conclusions from limited data. Well, data can be thought of as information, usually organized in some kind of fashion, and there is a ton of information and a ton of data out there. Some of it's organized, some of it's not. Apparently Google's mission is to organize all of the information and data out there. But you know, we have access to some data, okay? Let's say we had a simple question such as, what is the height of the average American male? Okay. What is the height of the average American male? Well, how can we answer that question, first of all? To answer that, we would first need to know, well, let's say I'm just talking about the mean here, okay? Mean being, you take a bunch of numbers, you add them up, and you divide by how many you have. Okay, so that's one way to find the average. And if I said, what is the height of the average American male, the only way to get a true answer to that is would be to record the height of all American males, so all 150 million plus American males. We would need the height of every single one. We would add all of those heights up, and then we would divide by 150 something million. Okay? And that would give us the average height of all American males, or the height of the average American male. But that would be practically impossible for us to do. Okay? We don't have the energy or resources to measure the heights of every single American male out there, and so we cannot answer the question that way. So instead, we are dealing with a situation with limited data. So rather than being able to observe every single person that we are technically interested in, we have to deal with what we call a sample. And so if we recorded the heights from maybe 1,000 American males, and we get the average height from 1,000 American males, does that provide us an answer or information about the answer to the original question of what is the height of the average American male? Okay. And the answer is it depends. It depends how we gathered our data and all of that. And we'll talk about that in a little bit. Okay. As you do your homework this week, when you read Chapter 1, Section 1, Chapter 1, Section 1 is all different examples of the types of questions statistics can answer, okay? Or would try to answer, I should say. And they're all coming from a life science perspective. So let's take a look at one of these examples here. Okay, this shows us, this is table 112. And this is the result of an experiment. Okay, and in this experiment, they took a total of 62 mice. And they wanted to know if the bacteria E. coli causes an increase in the rate of liver tumors developing in these mice. Okay, so they put the mice into two groups. Some they kept in a germ-free environment. Others they exposed to E. coli. And they had the mice live there. And then at the end of the experiment, or at the end of the experiment, they killed all the mice, cut them open, looked at their livers, and said, these ones have liver tumors and these ones don't, okay? I know that's a little cruel for the mice, but they did it in the name of science, so I don't know. I hope that's not too bleak here. But that's what happened, okay? So they took 62 mice. Some were exposed to E. coli, some were not. Some developed liver tumors, some did not, okay? And so at the end of the experiment, this is how they summarized the data. Okay, so they said some were exposed to E. coli, others were kept germ-free. Some developed liver tumors, others had no tumors. And here is the data. So, for whatever reason, they did not split the group evenly. They put 49 mice in the germ-free environment and 13 mice in the E. coli environment. 8 of them developed liver tumor. 8 out of the E. coli mice developed liver tumors, or whereas 5 did not. And as for the germ-free environment, 19 developed liver tumors and 30 did not. Okay. So based on this data, does it appear that exposure to E. coli increases the risk of liver tumors? Okay, and well, some of you guys are nodding your heads, and why would you nod your head?
Because a higher percentage of those mice were...
Yeah, okay, so if we look at how many mice develop the liver tumors in the E. coli, we would do 8 divided by 13, and we would get 61.5%. And if we do 19 divided by 49, we would get 38.8%. That's okay with everyone? Okay. So if it's good, nod your head. All right, and so we would look at this and we'd say, well, 61.5% of those mice exposed to E. coli developed liver tumors, and 38.8% in the germ-free environment developed liver tumors. And so therefore, or 61.5% is higher than 38.8%. Therefore, we might be inclined to believe that E. coli is associated with a higher risk of liver tumors. Does that sound fair or not fair? Fair? Maybe, maybe not? Okay, so let me just write that, and then I will say something else. Okay, so we say maybe. So I'm going to say this last sentence in statistics. So maybe in junior high or high school, that would have been a fine conclusion. Okay? At the end of this course, we will learn that we cannot jump to this conclusion immediately by looking at 61.5 versus 38.8%. Okay? One thing we have to look out for is that everything is different. Everyone is different. Every mouse is different. And so someone could argue that prior to this experiment, that a total of 27 mice were destined to develop liver tumors anyway. Okay? We had a total of 62 mice. At the end of the experiment, a total of 27 mice developed liver tumors and a total of 35 did not. We can see that, yeah? Okay, someone could argue, quite validly, that perhaps 27 mice were destined to develop liver tumors anyway. And that if we just created 2 boxes, we called one box A and the other box B, and they were identical. And if we just randomly mixed up the mice and we stuck 49 mice in box A and 13 mice in box B, just by random chance, it's very possible that out of those 27 mice destined to develop liver tumors, that 8 of them by random chance would end up in box B. Is that possible? Yeah, that's possible, okay? And if that were the case, then that means, does that mean box B is associated with a higher risk of liver tumors? No. All that has happened in this case is that just from randomly mixing up the mice, some of the mice happen to end up, a few more mice happen to end up in box B that developed liver tumors than mice that ended up in box A. Okay. So on one hand, it's entirely possible that this scenario that we observe is simply the result of random chance. Okay? That maybe the E. coli and the germ-free environment actually had nothing to do with the development of liver tumors, and these different rates of liver tumors is merely a result of just the random assignment of the mice. Or it's also entirely possible that E. coli is associated with a higher risk of liver tumors. Okay. So how can we reconcile these two possible outcomes, or these two possible scenarios?
You can repeat the study?
We could repeat the study, okay. That's certainly possible, but it could end up being quite expensive to do that. Okay. Well, one thing that we can do is we will use statistics to our, to our advantage here. And the idea behind statistics is that we have our data here, okay? And I painted a scenario with the box A and the box B, and 27 mice destined to develop liver tumors anyway. Okay? And I said in that scenario, it's possible that just from random assignment, some of these mice, that 8 of those 27 mice end up in the box B, or whichever box I labeled, the E. coli box, okay? In statistics, we're going to study some probability, and from that we're going to learn what is the probability of that scenario happening from random chance alone. And if it turns out that the probability of that scenario happening by random chance alone is high, then we cannot eliminate the possibility that it happened by random chance. On the other hand, if the probability that it will happen by random chance is extremely low, then perhaps it's safe to say it didn't happen by random chance. Okay. So let me just contrast this. So in this case, we had 62 mice, 27 developed liver tumors, and 35 did not. Just imagine another scenario. Okay, so I have, we're just going to call this A and this one B. All right, and in this case the boxes are not identical. There is a difference between them, but we don't know exactly what it is. And let's say some of the mice died and others survived. Okay. And at the end, 27 will die and 35 will survive. We still have 62 mice. And let's say the data turns out like this. Okay. In this scenario, someone could argue and say that when we randomly assigned mice to box A and box B, that 27 were destined to die anyway, and 35 were destined to survive anyway. Okay? And just by random chance, all 27 of the mice that were destined to die ended up in box A, and all 35 mice that were destined to survive ended up in box B. Is that possible? But is it likely? No. So something like this technically is possible by random chance, but it's so incredibly unlikely that we will say, whatever happened in box A probably is associated with what's killing these mice, okay? Even though we don't know what happened in box A and we don't know what happened in box B, the chance of this happening by random chance alone is so small, okay, that we can safely ignore that possibility and conclude that something is going on with box A, and something is going on with box B. But most scenarios will not be this clear-cut. There's a lot of gray area, and so by studying statistics, we will learn to see when we end up with a scenario like this, can we conclude that it happened by random chance alone, or if something is going on here. Yes?
Or that problem, the initial problem, does the sample size, like, is that like meant to show us what that sample size is irrelevant for the outcomes and the probabilities?
Okay, so sample size is very important. It's not something we have addressed yet. In this scenario, even though we have a relatively small sample size over here, we can work through it using statistics with something called Fisher's exact test and get an answer. And we can find out how likely is this scenario to happen from random chance alone. Okay. But we won't worry about that just yet. Okay. Are these examples okay? Are there any questions? Okay. So this is just kind of I guess, a peek or an illustration of where we are headed. Okay, and we'll get to here by about the 8th week. All right. And until then, there's a lot of, I don't know, not grunt work, but there's a lot of foundation laying. Okay, we're going to have to learn about just looking at data, describing data, learning the probability and all of that stuff first, and then we could start tackling questions like this. Okay, but this is just a little peek of where we are headed, and the rest of chapter 1, section 1 is also just kind of more examples of where we might be headed. Okay, it's all good stuff, but don't stress out too much. If any of the stories or examples sound particularly interesting to you, you can highlight them and then ask me, what is which chapter is this related to? Because this sounds like something I'm interested in. Okay. Okay, so let me just talk about gathering data. We can gather data in a few ways, and I guess the two ways, well, there's all sorts of ways to gather data, but we can classify them generally as either experiments or observational studies. In observational studies, we do exactly that. We observe. We We generally try not to interfere with the lives of the people we are studying or the subjects we are studying. And we just observe what happens. We take notes on what they do, or the conditions that they're living in, or whatever it might be, and we see what unfolds, okay? Other than but observing them in of itself may affect the subjects. So that sometimes is accounted for. Anytime you're looking at historical data that's already been collected, generally that will be a form of an observational study as well. Okay. Experiments, on the other hand, go out and actively gather the data, and we want to interfere with the lives of our subjects. Okay. So in an experiment, usually there's something that we're interested in. We want to know, what changes, what things might have an influence on someone's stress, or what things might have an influence on obesity, or what has, what influences this and that. Usually we have something that we're interested in, okay? That thing that we're interested in, whatever it is that we're trying to record, we call that the response, okay? The thing we measure that we are interested in that's called the response. And in an experiment, we try to think of all the different things that could have an influence on the response. Okay? And usually we have a question such as, does this influence the response? Does this one factor, does this one thing influence the response? So it could be, we want to know whether a drug helps reduce blood pressure. Okay. So if somebody has high blood pressure, we want to know, will this drug help reduce their high blood pressure? So in that case, the response is their blood pressure. We want to know what things influence blood pressure. And in particular, we want to know, does this drug influence it? Does this drug decrease that blood pressure? Okay. So we also, an experiment, there is a factor. And we usually call this the treatment. Factor, the treatment. And we want to know and or how it affects the response. Okay? But then there's also a bunch of other things that might also influence the response. Okay? Diet, stress, exercise, all of these other things might have a role in blood pressure. And so there's other factors involved. Okay? Other factors might also affect the response. So experiment, we try to control all of the other factors as much as we can, with the exception of the treatment. Okay? Or actually, we control that as well. So, but we try to control as much as we can, and we would set up two groups, a control group and a treatment group. And we would say, and we try to make both groups as identical as possible, with the exception of the treatment. So we would say, you know, everybody has to eat this diet, and everybody needs to do this much exercise, and everybody needs to have this much stress, or whatever, you know, whatever we can control, we try to control. And then we say, except this group is getting the actual drug, and this group is getting a placebo, which isn't supposed to do anything. And we're going to see how that affects blood pressure. Okay? And that way, at the end of the experiment, if we see a difference in blood pressure of the control group and the group that has the treatment, we can say, well, we controlled everything, and the only real difference between these two groups was this group got the control placebo, and this group got the treatment, and we saw that this group did have lower blood pressure at the end of the experiment. Therefore, we conclude that the drug indeed lowers blood pressure. Okay? That's what we want to do in an experiment. So other factors may also affect the response. Okay, so we control as many factors as possible. Okay, so that nearly everyone has the same conditions. Everyone has nearly the same conditions, I should say. Okay, except for the treatments. And if there is a difference between the treatment and control group, we can attribute that difference to the treatment. That is the general principle behind setting up an experiment. Okay, because if you do not do that, you don't control for all of these other things, or if you make no attempts to do so, maybe you will discover at the end of the experiment that the treatment group is different from the control group. But upon further study, it may turn out that the treatment group maybe was, I don't know, this would be a terrible example, but let's say the treatment group was all men and the control group was all women, okay? Well, at the end of that experiment, you don't know if the difference you observed is because the treatment made the difference, or if it was the sex of the subject that made the difference. Okay? Because if your treatment group was all male and your control group was all female, you don't know if whether it was gender or the treatment that makes the difference there. Does that make sense? Okay. So in an experiment, you want the two groups as identical as possible. Okay. So anyway, the major difference in terms of conclusions that can be drawn is that from an observational study, you cannot make a cause and effect conclusion. experiment is well designed and the data support it, you can make a cause and effect conclusion. But not all experiments are ethical. Not all experiments are practically possible. Okay? So if you wanted to do, we'll want to ask, does smoking cause lung cancer? And we want to perform an experiment to figure this out. One way to set up the experiment would be to get a bunch of volunteers and say, okay, well, thank you for volunteering for this experiment. And we randomly assign half of you to group A and half of you to group B. And starting tomorrow, group A is going to start, you will be required to start smoking a pack of cigarettes every day. We will follow you for the next 20 years and see how many of you develop lung cancer. In group B, you are not to go anywhere near cigarettes for the next 20 years, and we will see how many of you develop lung cancer. That would be a, quote, good experiment to see if smoking is associated with lung cancer, but it is not ethical nor practical to do. So sometimes an experiment cannot be done, and therefore you have to just do observational studies. Okay. Yes?
So then how come you say you can't make a cause and effect conclusion from an observational study if it is pretty established that cigarettes do cause lung cancer? Is that still like not proven then? It's not really experimental with it?
Okay, so even if we only do observational studies, so I guess from here I said, from an observational study, you cannot make a cause and effect conclusion, and that is 99.9% true, okay? There's like a whole, if you jump through a whole bunch of hoops, you might be able to make a cause and effect conclusion from an observational study, but generally you can't, okay? And actually, to answer that question, how do we know that smoking causes lung cancer? The truth is we don't really know for sure 100%. I mean, we're very confident, practically 100% confident. But for a long time, the tobacco industry would argue this. They would say some people were destined to develop lung cancer anyway. Okay, it was just in their genetics that they were going to develop lung cancer anyway. And it was the same thing that's in those genetics that caused these people to seek something soothing in their lungs, and that's why they were drawn to pick up the habit of smoking. Okay, it sounds ridiculous, but can you actually argue against that? Until it's kind of difficult. Okay, and we can do experiments on rats because I guess there aren't very much ethics about that, and we can say, oh, well, the rats that were forced to smoke cigarettes developed lung cancer, and then you could say, well, humans aren't rats, and we're different. So it's difficult to establish cause and effect without an experiment, and there's actually a whole field of statistics dedicated, and it's not actually statistics, it's called causality, and it's all the study of how can we establish cause and effect, because, well, the truth is we don't really know what causes things to happen. We see things happen and we say, oh, well, that causes that. And it kind of makes sense, but how do we really know what causes what? That's more philosophical. We're not going to get into that. Okay, so anyway, observational studies and experiments, a little bit more in your reading about that, okay? as for conclusions that we draw from a study, ideally, we want these conclusions to be generalized to the entire population. Okay? Now, the population in this case would be, everyone that we are interested in studying. Okay? So everyone we are interested in studying this is known as our population. But of course the population is too big for us to study directly. So, again, like I said at the beginning of the class, we are faced with a situation where we have limited data. So instead of studying the population, we study a select group, and that is called a sample. Okay, so we do not study the population. But a sample. And so the illustration that we always draw, because the population is this big thing, too big for us to study directly. We don't study that, instead we draw from the population a sample of size n. N is the sample size. Maybe n is 1,000, maybe we study 1,000 people. Maybe n is only 30, maybe we only study 30 people. Okay? Or maybe we study 20,000, however many people. Okay? N can be pretty much anything. And based on what we observe in the sample, we are hoping what we observe in the sample provides us information about the population. So prior to an election, we want to know what percentage, so let's say before a presidential election, or just any election, okay? For a presidential election, the election is determined, well, in the United States it's a little funny because we have the Electoral College, but let's just say it was a general popular vote, okay? We would want to know what percentage of the United States of voting Americans will vote for candidate A versus candidate B. Okay. Well, until election night, we don't know that answer, okay? So on election night, we get the answer of the population. We see what percentage of people who voted for candidate A and what percentage of people who voted for candidate B. But until then, we don't know what those percentages are in the population. But all newspapers, all groups like to make some kind of predictions, and so what do? They take surveys, they take samples. And based on these surveys and these samples, they make predictions. Okay, well, so let's say they survey 1,000 Americans who say they're going to vote in the election. What would that, based on what those 1,000 Americans say, can they make a prediction about the election? Maybe, maybe not. Okay, that's going to be like the answer for almost everything here. Maybe, maybe not. It all depends. Okay. Well, it all depends on who they ask for their 1,000 Americans, okay? If Fox News ran a poll on their website and they said, who are you going to vote for in this upcoming election? And let's say they got 10,000 responses. Would you trust those results to predict the election?
No.
No, okay. If the Huffington Post ran a similar poll and said, who do you predict will win the election? Would you trust those results? No, why not? As for either Fox News or Huffington Post's questions. Yeah, okay, because
Particular population.
yeah, you are not getting, because the people who respond to that poll are people who go to those websites